Hello everyone, I am Charles Chege. I'll be presenting to you the unit Probability and Statistics 2, BMA2102. I'm from the Department of Physical and Mathematical Sciences. First, we look at the objectives of we expect you to accomplish at the end of the unit. One, we expect you to be able to define probability mass, density, and distribution functions, and the use of them to determine the expectation, the variance, percentiles, and mode for a given probability distribution. Number two, we expect you to appreciate the form of probability mass functions for the binomial, geometric, hypergeometric, and Poisson distribution, as well as the probability density functions for the uniform, exponential, gamma, and beta, including the normal functions. We notice that there is the difference between the first list of distribution. These are discrete distributions, and the other list is composed of the continuous distribution. We are going to look at the difference between discrete distributions and continuous distribution. Number three, we expect you to be able to understand and apply the moment generating functions, or MGF, and the transform variable technique. And lastly, to apply the principle of statistical inference for one sample problems. Of course, this involves making inferences about a certain research. So in the first lesson, we are going to introduce random variables, both continuous and discrete, and be able to differentiate at what time are you supposed to be able to classify a random variable as discrete and the other time as being continuous. Now, first, we look at the concept of random variables. Now, a random variable is one that is determined by a random experiment. A random experiment is the one in which we cannot be able to tell an observation before we carry out the experiment itself. So first, a random variable must be obtained from a random experiment. Now, the difference between a discrete random variable and a continuous random variable is based on the type of the observation you make on the random variable x. Now, let's consider a case where you're carrying out an investigation and x is the ages of people. So you're going to collect information in terms of values that you read depending on what a person gives you a response to you in terms of their age, 20, 30, 40. Then if x, that is the random variable in question, is collected in such a manner such that it is countable or finite, then we say that it's a discrete random variable. And the other side, you might be collecting information about a research, and you can only categorize the random variable as an interval. Say x lies anywhere between 0 and 1. We should note that there are an uncountable number of values we can collect in the interval 0, 1, including 0.5, 0.1, 0.02, 0.001. All those values are in the interval 0, 1. So if the random variable in question in a certain experiment can only be observed in terms of an interval between two extreme observations, then we say that it's a continuous random variable. In any type of question you will deal with in probability distributions, it is important first to deliberate and be very keen on what type of random variable you're using, because it determines then from there what distribution you will associate with that random variable. Now, an illustration of discrete random variables, and we note that most discrete random variables will have an associated probability mass function. Actually, a probability mass function is a function, sometimes a table or a graph, that generates corresponding probabilities of that random variable in question. If x is 10, what is the chance of getting that 10 if I carry out the experiment? So a probability mass function, PMF, will give us corresponding probabilities of a discrete random variable. Now, consider the experiment of flipping a coin 3 times. Again, the number of tails that appear is noted as a discrete because you can have 0, 1, 2, or 3 tails. Let x be the number of tails that appear in 3 flips, so that the total number of outcomes is as follows, and there are 8 of them because the relationship in the number of tosses of a coin is such that the outcomes you get is 2 raised to the power number, to the 2 raised to the number of coins you toss, that is 2 raised to power 3, and that will give you 8. So this is the list of the possible outcomes you can get. You can have 3 heads, 2 heads, then head, tail, head, in that order. And we notice that there is only one case without a tail. That is the situation where all the 3 coins show up as heads. Then we have this case where we have just a single tail. You get a head, then a tail, you get a head, a tail, then a head, and then in this case where you get a tail, then followed by a head, followed by a head. In the case where we have 2 tails, it's this case, and this case. And lastly, you can toss the 3 coins and none of them shows a head. So we'll have a total of 3 tails. This shows the set of all the possible outcomes. And the corresponding values taken by the random variable x then are 0 when you have no tail, 1 when you have a single tail, in which case we have 3 possible options. Then the other case where you only have 2 tails, which we have this case, and this case, and this case. And if you tally, then you get 8. So that each of these outcomes can be considered out of the total number of outcomes you get. Now, the possible values of x, the possible values x can take are x is equals to 0, 1, 2, and 3, and we can then come up with the probability distributions corresponding to it. And now, if you come up with such a table where you have the values of x and the probabilities you can get, or the probability of getting that value of x, because we noticed that we had only one case where we didn't have a tail. And out of the total 8, then that one case is what is making us to write here 1 out of 8, because only one case out of the 8 cases. Tails, 1 tail only, there were 3 cases, and 2 tails only, there were 3 cases again, and only 1 case didn't have a tail. And only 3, so only 1 case had 3 tails. So we can then associate each observation of x as a random variable with a corresponding probability. And I'm saying that this table now makes a probability mass function because it can give us probabilities corresponding to these random variables. Note, PMF, probability mass function, is associated with discrete random variables. And as we had suggested as we were beginning, then we can use this distribution to be able to determine the expected value, the variance, and some other statistics like quartiles, mode, and median once we are having such a distribution, so that we can say that the PMF places the mass of 1 over 8 on the value x, or 3 over 8, or the value x is equals to 2. The masses of probability should be between 0 and 1. And that is a very important aspect of probability, that if you have a PMF and you have the corresponding probabilities, the ones we are calling P, x of x, this just implies that it's the probability that the observation, the random variable x, will be associated with the value x. If you have several of them, let's say we have, I labeled them with some subscripts here, we have pi of them for I is equals to 0, 1, 2, and so on, then all the probabilities you'll have for a certain random variable will be such that if you sum them, if you sum probability I starting from 0 to n, assuming that we have n of them here, then you're supposed to get 1. At any given case, if you have a probability distribution function, these have to hold for all random variables. So in our case there, we are having x, and then the corresponding probabilities of x. We have 0, 1, 2, and 3, and we have 1 over 8, 3 over 8, 3 over 8, and 1 over 8. Then for us to satisfy that this table represents a PMF, then we need to show that if we add all these probabilities corresponding to these observations of x, they add up to 1. So we need to show that summation x, or rather I starting from 0 to n of P of I is actually 1. And we can see that 1 over 8, the first probability corresponding to the first observation, plus 3 over 8, plus 3 over 8, plus 1 over 8 is actually 8 over 8, which is 1, which actually qualifies this table. It qualifies the table given here as a PMF, as a probability mass function. Now, this just insists on the properties we've talked about. That another important property is that probability of any given random variable x must lie between 0 and 1. So it would be absurd for someone to give a solution to a probability question as being outside this interval, like say -1/2. You can't give the probability of an observation of x being a negative value or a value greater than 1. That would be a case where you have overlooked something, or you just need to go back and check what was the problem. Now, we can generalize things here. One, it is a discrete that can only, a random variable is such that let x have the following properties. 1, it is a discrete random variable that can only assume values x1, x2, all the way to x1. Like in our case here, we are saying our x1 is 0, our x2 is 1, and our x3 is 2, and our x4 is 3. So this just implies the number of the observations in x that you expect in that given experiment. Number 2, the probability associated with these values must be such that the first observation is associated with the first probability, the second observation to the second probability, like in this table. Each observation with a corresponding probability is giving us the chance that it will be observed. A remark here, we denote random variables with capital letters, while realized or particular values are denoted by lowercase letters. So the observed values of x will be abbreviated with a lowercase x and a uppercase x to represent that specific random variable. Let's look at some examples here. Now, two tetrahedral dice are rolled together, one, and the sum of the scores facing down are noted. So we are going to toss 2 tetrahedral, implying that they have 4 sides, and we'll assume that those 4 sides are labeled 1 through to 4 in both cases. So we can have this being the first dice, we call it x, so that it has 1, 2, 3 as the numbers labeling its sides. Then we can have another one here, call it y, so that it has 1, 2, 3, and 4. So we want to roll these tetrahedral dice, and then whatever we get on the lower side of the dice after it settles, we add them on the 2 cases. So the options we are having here is that 1, both dice will show a 1 and a 1 on the lower side. That's the first case. So that if I sum this and this one and this one, I get a 2 here. Now, if the first dice shows 2 and the second one 1, then I'll have a 3, and then I'll have a 4, and then I'll have a 5. Then we can have the case where the first dice is showing 2, so that this one is changing. So we are going to have this is 3, this is 4, this is 5, and this is 6. And then we can have this plus this being 4, 5, 6, and 7. Then in this case, we can have 5, 6, 7, and 8. So whatever is enclosed here represents what we call the sample space, or the total number, or the number of observations we can make by summing the observations on the lower side of the 2 tetrahedral. And from here, we can look at a PMF we can obtain from here, from this set of observations from the 2 dices. So we will create a table with all the number of observations we can get, call them x, all the observations that we can get we label them X, and then we can have a table representing the number of observations corresponding with their probabilities. So from here, we are observing that we can only have the sum total being 2, only one case out of the 4 by 4 cases we are having, which is 16. So 2 occurs only once out of 16. So that's why we are saying when X is 2, the probability of getting that 2 is 1 over 16. Then 3 is occurring twice. So 2 out of 16. Then 4 is occurring 3 times. So we have 3 over 16, and so on until the last observation, 8, occurs only once out of 16. So this is now a PMF. And this PMF can generally be written as X minus 1 for values of X in these tables, which are 2, 3, 4, and 5. So if you're using the upper part of this distribution given here, then it's only for the cases 2, 3, 4, and 5. But for 6, 7, and 8, we use the case 9 minus X over 16. By applying this for these values of X, you're going to get this table. So these and these represent the same thing. They are PMFs for our case of tossing 2 tetrahedral. Now we look at examples which we derive together here to see what they imply. So in the first example, we have a random variable W, and the corresponding probabilities, W is equals to W. You're given that W takes -3, -2, -1, then it takes 0 and 1. And the corresponding probabilities are 0.1, 0.25, we have 0.3, and we have 0.15, and then finally we have D. So the first question is, you're told to find the value of D, this first part of the question. Find the value of the constant D. Now, to be able to solve the first part of the question, we remember that summation of all values of X, of probability of X, is equals to X. You say that this has to be 1 for this to be said to be a PMF. So that means if we sum all the probabilities, we are going to get 1. So 0.1 plus 0.25 plus 0.3 plus 0.15 plus D should be 1, so that it is a PMF. And therefore, we can see that we only have one unknown as D, which we can solve. If you add all through, you get 0.35 plus 0.45 plus D is equals to 1. And then this now becomes 0.8 plus D is equals to 1. And therefore, D must take 1 minus 0.8. And therefore, D is 0.2. And we can see clearly that since D is 0.2, it qualifies for the properties of probability. We've said that probability of any given case, as you can see from these ones, must be in the interval 0, 1. So since this is in the interval 0, 1, then we can be able to conclude that it's a PMF. Now, after getting the value of D, we can now check the other parts of the question that we are given. We are told to find the probability that W lies in the interval -3 included and 0 not included. So we have to go back to our table and see what that means. So we are told that we should get the probability that X is in the interval -3 and 0, -3 included, but 0 not included. And therefore, we are looking at the cases where W is -3. Because this is a discrete case, we can pick specific points. We are also looking at the case where W is -2, looking back at the table there, and we are looking at the case where W is -1. So we are not going to include 0 in this case because we are told not to include. We have this small interval given here. So this means we are looking at probability W is -3 plus probability W is -2 plus probability that W is -1, which are given in the table there, the first 3 probabilities. So we have 0.1 plus 0.25 plus 0.3. So this becomes 0.65. Then the other part is probability that W is greater than -1. So according to the case there, then because -1 is not included, then we are looking at the case where W is 0 and probability that W is 1. So in that case, we have 0.15 plus 0.2 because we already got the value of D as 0.2. This is 0.35. Then the last part, we are told to get the probability that W is either in the interval -1 and 1, both not included. So looking clearly, between -1 here and 1, if we are not including the 2, then we only have one case. So in other words, another way of putting this is that probability is getting the probability that W is just equals to 0. There is no any other observation of X that is in this interval. So this is simply 0.15. Then we have another example there. We are told that a random variable Y has a PMF given by the table this. We notice that the table has Y and the corresponding probability of Y with unknowns. So we first apply the concept of the summation of probabilities in a given case must be equals to 1. And clearly, if Y and probability Y is equals to Y is given as 0, 1, 2, 3, and 4, with probabilities C, 2C, 5C, 10C, and 17C. If we apply the concept of summation of all X of probability of X is equals to X is equals to 1, then we can get that C plus 2C plus 5C plus 10C plus 17C should be equals to 1. Since again we have only one unknown, we can be able to get the value of C because this is 3, 8, 18, 17, so this is 35. C is equals to 1. And therefore, if we divide both sides by 35, so that we remain with our C, with the value C, we have C is equals to 1 out of 35. So that is the value of the random variable. And we can be able to apply that then to compute the probability that Y is in the interval between 1 and 3. And 3 is not included. So that means we will need the values of Y when 1 and when 2 only, because we don't want to include 3. So we are told to get the probability that Y is in the interval 1, 3, 1 included. So this is actually the same as getting probability that Y is 1 and, or probability that Y is 2. We are not going to include 3 because of this limitation. It's less than, not less than or equal to. So in this case, we have 2C plus 5C. But we already got C. So this is the same as 2 times 1 over 35 plus 5 times 1 over 35. And therefore, this is 2 over 35 plus 5 over 35, which is actually 7 over 35. Now, we can proceed to the next thing. We have a set of questions here for attempt. Then we can look at continuous random variables. And for continuous random variables, they are associated function, table or expression that can give the corresponding probabilities is called PDF, probability density function. Notice that previously when we had discrete random variables, we had PMF. So in this case, we call them PDFs. They give us the corresponding probabilities of a given random variable for the case where the observed random variable is in an interval, that is, it is continuous. So these continuous random variables can assume any value in an interval or a real line or in a collection of intervals. So you can have different intervals being given for a different set of observations in Y. Now let T denote the time that lapses before the first arrival. Then T is continuous random variable that assumes values in the interval 0 to infinity 0. This expression just means that 0 is included, but infinity is not included. We don't want to include infinity because in this case, infinity is considered to be undefined. So we are saying T can take any value between 0 and any value that can be determined. So a random variable x is continuous if there exists a negative function f, so that for every interval b, this holds. That is, if I want to get the probability that x falls in a certain interval, that is probability or a certain value, probability that x is equals to a certain constant, then f of x being the function, I'll have to integrate from over all b f of x dx. If this holds, then we say that x is a continuous random variable. Then the function f is called a PDF. As I was stating earlier, that for the case of discrete, we have PMF. For the case of continuous random variables, we have PDF. Now, another definition here. Let x be a continuous random variable that assumes values in this interval, that is negative infinity to infinity. F of x is said to be a PDF, a probability distribution function of x, if it satisfies the following conditions. Number one, f of x must be greater than 0 for all x. Then, if you want to get the probability in the interval between a and b, like the ones we were doing for discrete, in this case for continuous, in the other case we were summing. So in this case we are going to be integrating over all sets of in the probability, then the distribution with respect to x. If this is 1, then it's truly a PDF, because for us to check in the other case, for us to check in the previous, in the PMF set, we were talking of summing of our values of x. That is replaced with integrating from negative infinity to infinity. That is all the possible sets of values of x. If it is 1, then we'll use it to confirm that it's a PDF, like the way we were using the summation of the probabilities. But if I want to get probability that x lies in a certain interval, I just integrate over that interval the PDF to get the corresponding probabilities. We look at some remarks. A crucial property is that for any real number x, we have probability of x is equals to x, implying that there is no difference between the random variable and the observed. So they give us the same thing. That is, it is not possible to talk about the probability of the random variable assuming a particular value. Another remark, instead, we talk about the probability of the random variable assuming a value within a given interval. So we will be talking about an interval. Even if I say x is greater than 0, then I'm implying that x is lying between 0 and infinity. It's not that I don't have an upper limit. So within some given interval from x is equals to a to x up to b is defined to be the area under the graph of the probability density function between x is equals to a and x is equals to b. And that is the probability we'll be calculating. We can now look at some examples. You're given that a random variable x, f of x, a half x, for the interval 0 to is it can be considered as a PDF. So we should compute probability that x is in the interval 0, 1 and probability that x is negative 1 to 1. Now, if f of x is given as a half of x for x in the interval 0, 2 and 0 otherwise, then we've said that if you're looking for the probability that x lies in the interval a to b, then this simply means you integrate from the lower limit of x, that is a, up to the upper limit of b, of the expression of the PDF with respect to x. This automatically gives you the probability that x is in this interval. In our case, we want to find the probability that x is in the interval 0 and 1. So this will mean that we integrate from 0 to 1 of our PDF f of x dx, of which we will have integral from 0 to 1 over half of x dx. The integral of this is 1 over 2. Then since the power of x here is 1, we add 1, then we divide by that. So this will mean divide by 2 again, then x raised to power 2. And then we replace our limit 0 to 1. So this will mean 1 over 4, because we are dividing a half by 2. Then x squared, limit 0, 1. So we start with the upper limit, so 1 over 4. Then if I put 1, I have 1 squared. If I put 0, I get 0 squared. So it's actually a quarter, which is in the interval 0, 1. Hence it qualifies as a PMF. Now, in the other question, we are told to get the probability that x is in the interval negative 1 and 1. This means we integrate from negative 1 to 1 of f of x, which is a half of x with respect to x. So this is the same as 1 over, because we've already integrated this. So it will imply 1 over 4x squared, negative 1 to 1, which is the same as getting 1 over 4, then 1 squared minus negative 1 squared. So this is the same as a quarter. Then we have 1 minus 1, which is actually 0. So the probability that x will lie in the interval negative 1 and 1 is 0. And clearly, if we observe this interval, the interval is 0, 1. So we have gone beyond the lower limit of our PDF. And that's why we are getting this, which in probability means that it is not possible for this to happen, because the PDF is defined outside this interval. This interval is outside our expected values of x, and that's why we are getting something that is not possible to work. Now we have another example here. The time x in hours between computer failures is a continuous random variable with this density. We are told to find lambda, whatever is here in the expression, and hence compute those probabilities. Now, we are given that f of x is equals to lambda exponential negative 0.01 of x, and we are told that x takes values from 0 to infinity and is 0 elsewhere. And therefore, first, we've said that if this is truly a PDF, then it should have the probability that integral over all values of x from negative infinity to infinity of f of x dx should be equals to 1. by doing this, by confirming this, we are showing that it's truly a PDF. So let's check. This property will help us to know what is this, so that it qualifies for this property. So we are going to have integral. You can see the values of x are not starting from negative infinity rather, but they are starting from 0. So we'll start from the lower limit of x, which is 0, up to the farthest we can go is infinity. And this means x is from 0 all the way to undefined. So lambda exponential negative 0.01x dx should be 1. If we are able to find lambda such that this expression gives us 1, then we will have found a value of this to make it a PDF. So first, we can factor out lambda. Since it's a constant, it does not depend on x, so that we remain with integral 0 to infinity of exponential negative 0.01x dx is equals to 1 again. But here, we have to go back to calculus. The integral of an exponential function with respect to x is the same as 1 over the derivative of that function, then the same. You just write the same. So in our case, we had integral 0 to infinity, lambda, we factored out lambda, exponential negative 0.01 x dx is equals to 1. So in this case, to differentiate this exponential function, we are to integrate this exponential function, we are going to differentiate the power of the exponent with respect to x, which remains 0.01, because the derivative of 5x is 5, so the derivative of negative 0.01x is negative 0.01. So we are going to have lambda, then 1 over negative 0.01, then exponential the same, negative 0.01x, then place limit 0 to infinity. This should give us 1. So that, clearly, this is the same as lambda negative lambda all over 0.01. Then, if I put limit exponential, I'll have negative 0.01x times infinity, which is actually negative infinity. So I'll have exponential negative infinity minus, if I put x as 0, I'll have this, the whole of this becoming 0. So I'll have exponential 0. So this should give us 1 again. So we are having negative lambda all over 0.01 is equals to, now exponent of a negative infinity is actually 0 minus exponential of 0 is 1. So in that case, this should give us 1 again. So we are having negative lambda 0.01, then we are having 0 minus 1 is equals to 1. So this would make this to be a positive number, because this times this is 0, then this times this will make a positive. So we have lambda all over 0.01 is equals to 1. And therefore, lambda, by cross-multiplying both sides by 0.01, we have that lambda is 0.01. So it means that our expression is supposed to be f of x. Our PDF is expected to be 0.01 exponential negative 0.01 x for x greater than 0 and 0 elsewhere. And therefore, we can be able to use this PDF and to answer the other parts of the question. That is, we can get the probability that x is between 50 and 150, probability that x is in the interval 50, 150. From what we have already defined, then this is the same as integral from the lower limit to the upper limit of f of x dx, which is actually the integral from 50 to 150 of 0.01 exponential negative 0.01x dx. So we can again factor out 0.01, so that we have integral here will be negative 1 over 0.01 exponential negative 0.01 x. Then put limits 50, 150. And of course, this will be 0.01 divided by 0.01 negative, then exponential negative 1.5 minus exponential negative 0.5. So placing this in the calculator, you'll get the corresponding probability of x. In the last example here, a continuous random variable x has a probability density function given by f of x is equals to 0.25 when x lies between 0 and 2. Then we have another expression, 0.5 x plus c when x lies between 2 and 3, and it's 0 for any other interval. So first, you have to find the value. See, as we've said, for you to be able to get this, you need to apply the property that for any PDF, integral from negative infinity to infinity, that is over all values of x, dx, should be equals to 1. So we need to integrate each of these with respect to the corresponding intervals. So integral from 0 to 2 of 0.25 with respect to x plus integral from 2 to 3 of 0.5 x plus c with respect to x should be equals to 1, because we are using this property. Now if I integrate this with respect to x, I get 0.25x, put limits 0 to 2, plus if I integrate this with respect to x, I can split the 2, so that I have, that will be 0.25 divided by 2, then x squared plus cx, then we put limits 2 to 3, which should give us 1. So these, if we put 2, it will be 0.5. If we put 0, it disappears. Now, we come here and put 3, then I'll have 0.5, or I can simplify first. This is 0.25 x squared plus cx, put limits 2 to 3 is equals to 1. Then from here we can now put the limits for the other part. We'll have 0.5 plus 0.25 multiplied by 3 squared plus 3 times c. Then the whole of this is supposed to be subtracted from 0.25 multiplied by 2 plus 2 times c. This should give us 1 again. So that's 0.5. This is 9 times 0.25, which is 2.25 plus 3c minus, this is 0.5 plus 2c is equals to 1. And this is 7.25 plus 3c minus 0.5 minus 2c is equals to 1. So that we have, this is 6.75 plus c is equals to 1. So that c is equals to 3.25 by taking this to the other side and subtract it. So this is the value of c, that would make these a PDF. And of course, from the property that when you getting the probability between 1 and A and B is integral from A to B, you can be able to get. You notice that these will capture both this and this. So if then we are looking for the probability that X is in the interval 1 to 2.5, then these will have to be split because it captures both parts of that piecewise function. So first we can integrate from 1 to 2 because it lies in the first part. So we will integrate from 1 to 2 of 0.25, then plus with respect to x, then plus integral. The other part now from 2 to 2.5 lies in the second part. So we will integrate now from 2 to 2.5 of 0.5 x plus c, which we got 3.25. And then you integrate this, whatever result you get, you add to this to get the corresponding probability in that interval. We have a set of questions here for attempt. Each of these is given either as piecewise function or a single function, and it is just testing the properties that we've had. You're either getting the probabilities, getting the constant, or you're getting m so that this holds. You notice that this is from 0 to 1. So if you're told x less than m, and this is a half, then you're going to integrate from 0 to m so that the answer is a half, and so on. So that is the end of lesson 1.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.